So we're going to take a look at some factoring techniques that we've already seen before in some previous classes, and just kind of try to remember what we're doing with them so we can utilize them in some other topics a bit down the line. So what is factoring? Factoring is essentially taking an expression and turning it into a multiplication problem. So for example, if we have two binomials being multiplied together, that's what we think of as multiplying, or sometimes we say foiling or double distributing. But reversing that process, right, undoing those distributions, is what we call factoring. So taking that trinomial that we had here and turning it back into these two binomials being multiplied together, that's what we consider factoring. So the most basic type of factoring that we see is factoring a GCF. This is the type of factoring that we always want to look for first in any factoring problem. It's what's going to allow us to simplify a polynomial to the point where we can use other techniques as well. So when we're looking at a GCF, first you just want to look at your two terms separately and kind of determine what would be the GCF of those terms, so greatest common factor. So look at the number parts first, so 12 and 6. The largest number that both 12 and 6 are divisible by is 6. Right? So it's okay if it is one of the numbers that is a coefficient of one of our terms. And then we want to look at the variables. And whenever we're looking at a GCF of variables, we're always looking at the most number of any particular variable that they have in common. So both of these terms have an x to the first. So the GCF here would be 6x. So if factoring is essentially the undoing of multiplication, we use division in order to kind of facilitate that. So we divide each of these terms by our 6x, right? The 6x becomes what we're multiplying, and then we have the leftover bits, which is what we have after we factor or pull out that 6x from both of our terms. So here we would have a 2x minus, now be very careful, don't write just nothing here, don't write 0. Anything divided by itself is 1. So in this case, we would have a minus 1. We do need a placeholder for that because if we go to check our work, the way we do that is by distributing back in to see if we get the polynomial that we started with, right? So if I distribute back in, I get 12x squared minus 6x. And if I didn't have anything right here in this second term spot there in that binomial, I wouldn't end up with what I started with, and that would be a problem. So just always make sure to watch out for things that simplify to 1, and always make sure that anything you factor out stays with you throughout all of your work, because we need to be able to multiply it all back together at the end to check that we get back to what we started with. That's kind of the point of factoring. We're just taking something, a polynomial, and pulling it apart into its sort of component pieces, right? So let's take a look at a few more types of factoring. So another thing that we factor very often are trinomials, right? So for this, we can take just a quick look on the side of what happens when we get a trinomial from a multiplication problem, right? So say I have x minus 2, x minus 4, right? If I multiply this together, I'm going to end up with x squared minus 6x plus 8. Now something that we can see here is that we would get this 8, right, this value 8 here, by multiplying negative 2 times negative 4. And we get this middle term value here by adding negative 2 plus negative 4. So we're going to use that in reverse to kind of create the two binomials that we would get by factoring a trinomial. All right, so hopefully some of this is looking familiar to you from your Algebra 2 course here. All right, so here's our trinomial. So oftentimes we can even think back to when we were multiplying binomials to that FOIL acronym there, right? First, outer, inner, last. So your first term times your first term will always be your first term in your trinomial. So my first term here in my trinomial is an x squared. So I know first times first, x times x must give me my first term in my trinomial, or my x squared. Next, we're just looking for two numbers that when we multiply them together, we get a positive 8, but when we add them together, we get a negative 6. So in this case, our two numbers would be -2, -4. So it was actually just a coincidence that my other example worked out there. So we were just reversing it, and that's how we reverse it. So we cannot forget about that good old greatest common factor. So if I look at the next one, I can see that all of these terms are divisible by 2. So I do want to factor out that GCF first before I worry about anything else. So I'm going to divide each of these terms by 2. My GCF goes out front, left with x squared plus, I don't know why I wrote a p there, it should be an x, plus x minus 2. So now that I've factored my GCF out, I now have the GCF out front, and I have a trinomial. And that trinomial I can factor further, right? So this is a multi-step process. So now I have 2, and I'm going to factor that trinomial into my two binomials, right? So I always have first times first gives me first, and my first here is an x squared. The only way to get an x squared is to take x times x. Now, I need to multiply out to a -2, but add up to a positive 1. So one thing you can always do is just write out your factor pairs in the number. 2 is a prime number, so I only have one option here. 1 times 2. And I know that I need a -2, so I know that one of these values has to be negative. So I know one of these numbers has to be positive, one of these numbers has to be negative, and my options for these numbers are 2 and 1. Those are my only options. So in this, if I write +1 minus 2, if I added that together, I would get a -1, which is not what I want. I want a +1, right? That's the coefficient of my linear x term. So instead of doing that, I will instead say, all right, well, really, I think I want +2 minus 1. Now when I add them together, I get that +1, but they still multiply out to that -2. All right, and we've factored a trinomial. All right, so what happens when our leading coefficient, right, the number in front of the x squared, is not 1, and it also does not factor out with a GCF? So a couple different ways to do this. First way, it'll factor into two binomials. You can just guess and check what the values should be. But the more methodical way to do this is, a lot of people call it like the bridge method. So essentially what I want to do is similar to what we did before. We want to take 2 times 6 here, right? First times the last, and that's going to give me 12. Now, this time, I'm going to be asking myself, what two numbers multiply out to 12 that add up to our middle term's coefficient of 7? So again, we can write out our factor pairs to help us. 1 times 12, 2 times 6, 3 times 4, and then we can look at which set of numbers is going to work. And here I can see that's 3 and 4. Now we're going to use this to break up that middle term and factor by grouping. All right, so I'm going to break up that middle term. I'm going to say this is really 2x squared, and then 7x is really 3x plus 4x. But I'm not going to write it in that order. I'm going to write the 4 first because the 2 and the 4 have a factor in common. I'm going to write plus 4x plus 3x plus 6. So all I've really done is changed what that middle term looks like, right? And I've split it up into 2. Now what this allows me to do is to group, right? So I can group my first 2 terms, group my second 2 terms, and I can see that they have a common factor, and I can factor it out, right? So that GCF idea comes into play quite a bit. All right, so I'm going to say, well, these first 2 terms, they have a common factor of 2x. So I'm going to factor that out. So 2x, and then what's left over, all right, x plus 2. These next 2 terms have a common factor of 3. All right, well, plus 3, and then what's left over, x plus 2. And now what I can see is that we have 2 binomials here, and they're identical. So now we kind of have 2 terms, right? And they have a common factor of a binomial. So I can factor that out, and I'm left with 2 binomials when I'm done. So we have our x plus 2, right? That's the common binomial that we can see right off the bat. And then the coefficients, right, the bits in front of those binomials, we can kind of call them coefficients, create our second binomial. So 2x plus 3 would be our second one. All right, and now it's fully factored. So let's try another one. So always looking for a GCF first. In this case, we don't have one. So we do want to go ahead and factor this out. So we'll just go ahead, multiply first times last there. All right, so that's a negative 60. So we're looking for two numbers that when we multiply them, we get a negative 60. But when we add them, we get a negative 17. And sometimes an easier way to do this is instead of looking at factors of 60, look at factors of 5 and 12, and you're going to try to create combinations from them. So I'll do a little bit of an example of that. So I'll kind of do my work a little bit down here. So if I have 5, right, its factors are 1 and 5. And 12, we have 1 times 12, 2 times 6, 3 times 4. So I essentially want to take some combination of these three numbers and then get two numbers from that. It's a little bit weird, but a little bit easier than looking at so many factor pairs of 60. So what I can see here is that, all right, well, 5 and 3, that makes 15. And then we have a 4. Well, 15 plus 4 is, well, that's 19. So that's not quite going to work, right? But that's kind of the idea of what we're trying to do here. So let's try that elsewhere. All right, so we're close, right? We're close, but not quite right where we want to be. So let's try another one. Let's see. We could have, let's see. If we work with the same factor pair here, so if I work with the 5, the 3, and the 4, but if this time I take 5 times 4, well, that's 20. And what is really important about that is that the other one is 3, right? Okay, well, I want 17. Well, 20 minus 3 is 17. And I do want to multiply out to a negative 60, right? A negative number. So I know that one of these factors needs to be negative. So if I make this a negative 20, then when we add them together, we do get that negative 17. So I want to be working there with negative 20 and 3. So it's just a little bit of a different way to be working with that. So then if I look here, negative 20 times 3 is in fact that negative 60 that we were looking at when we multiplied out. So we're going to do the same deal. We're going to factor by grouping. So I'm going to split that middle term. The first one I'm going to write is with the 20 because 5 and 20 will have a common factor. So we'll say minus 20x plus 3x minus 12. Now, if you want to work with the factor pairs of negative 60, go for it. It just depends on what works best when you're thinking about it in your head. All right, so we'll factor out greatest common factor. This first one is 5x. The second one we can factor out a 3. Right, then we have our common binomial, and the leftover bits make up our last binomial. All right, we always do want to keep in mind that sometimes we're going to need to factor a greatest common factor here as well. So here in number 3, I'm going to factor the GCF out of 2. Right, and now we're looking at factoring this trinomial here. Okay, so we're still going to have our GCF, and we know it's going to factor into 2 binomials. And we just need to sort out what values are going where, right? And we're going to do this through grouping. So I'm actually going to get rid of those. So let's see, 3 times negative 8 is going to give us a negative 24. So now we need two numbers that when we multiply them together, we get a negative 24, but when we add them together, we get a negative 2. So we can come up with a couple of factor pairs. The one that's going to work is 4 times 6, and I need when we add them together, we get a negative 2. So I'm going to make the larger value my negative there. Now we can sort out grouping. So 3x squared minus 6x plus 4x minus 8. So all I did is rewrite that middle term, -2, as -6x plus 4x, right? Same thing, looks different. And now factor by grouping. So this is where we can use some different types of brackets to indicate multiple sets of parentheses. It's just a little bit easier to use brackets rather than multiple parentheses. So I'm going to have 2 times the quantity and factor out our GCFs. So we're going to have factoring out of 3x here, and we'll be left with x minus 2. Factoring out of 4 here, and we'll be left with x minus 2, as we were hoping. So close our braces there because we're done. So you just want to keep in mind that that 2, that GCF, is being multiplied by everything in there. So when we start factoring by grouping, we do need to keep everything together as we're doing that. So now we can go ahead and simplify this. So 2 times our first similar binomial there is that x minus 2. And then the next one would be the 3x plus 4. At this time, because everything is being multiplied, right? Each piece is being multiplied. So we have 2 times the quantity x minus 2 times the quantity 3x plus 4. I'm allowed to drop those braces because multiplication is commutative. And we don't need to be distributing like we did in the previous step because of that addition symbol. Okay, so sometimes there's a special case for trinomials. They're called perfect square trinomials. So we have 2 kind of generic situations here, right? We have a squared plus ab plus b squared, and we have a squared minus ab plus b squared. So our first term and our last term must be perfect squares. So if I look at number 1, I can see that 16 and 9 are both perfect squares, and really x squared as well. So anything with an even exponent, any variable with an even exponent is a perfect square. So I'm allowed to factor this using the rule of perfect square trinomials. All right, so I want to try to come up with sort of this rule through example. So I'm going to multiply 2 binomials. I'm going to show you kind of what happens here real quick. So if I take 2 binomials, let's say 2x plus 5 times itself, 2x plus 5. Let's see what happens. So we'll end up, double distribute. So we'd get 4x squared plus 10x, distribute again, plus 10x plus 25, combining like terms, 4x squared plus 20x plus 25. Now, what I can see here is that the end term, right, the 25, is a perfect square, right? 5 times 5, right? So these 2 numbers were just the square root of 25. And this first term, 4, is 2 times 2, right? And the square root of 4 is 2. So that's how we're going to determine our 2 binomials, right? And you can see we were adding our middle term as positive. So this is the generic case here. This is equal to a plus b squared, right? The same thing, so something times itself. So we're going to factor this guy. So we said, okay, 2 binomials. The first term we get by taking the square root of the first term in the trinomial. So square root of 16 is 4, square root of x squared is x, and that's going to duplicate over here. And the last term we get by taking the square root of the last term. Square root of 9 is 3. Now, we need to consider the signs. So this still follows the same rule, multiply to the last term, add to the middle term. The last term is positive, the middle term is positive. The only way to do that is to have 2 positive numbers. Positive times a positive is a positive, positive plus a positive is a positive every time. So I want plus and plus, and we do want to rewrite this because something times itself. We have a way to write that more concisely using exponents. So this is really 4x plus 3 squared, and that's how we should write our final answer. So let's take a look at another one of these. So Again, you want to remember that we have a greatest common factor sometimes, and so you want to factor that out where possible. So as it stands now, example 2 is not a perfect square trinomial. 36 is a perfect square, but 64, well, 64 is, no, it is a perfect square trinomial, my apologies, but it's not a simplified perfect square trinomial. So we want to simplify it first. And this is one of those cases where you really got to be on the lookout since it is a perfect square trinomial, but there also is a GCF. And we always prioritize GCFs first. So our GCF here is 4. So we're going to factor that out. We're going to get 9x squared plus 24x plus 16, right? So if you don't factor that out at the end, you're not going to have the most simplified version of your polynomial, right? You'll have to kind of factor again. And it's just kind of messy. So now we want to factor this. So I'm just going to immediately go to that squared notation. So we know it's a perfect square trinomial. So we know it's going to be a binomial squared. First term is square root of the first term in the trinomial. So 3x. Last term is the square root of the last term, or 4. So square root of 16 is 4. And then the sign is determined by the sign of your middle term, right? Because the only way we can get that positive when adding as well as a positive when multiplying is if both numbers are a positive. All right, so that would be our final answer. All right, so next one, this does not have a GCF, so we can go straight to factoring as if it was a difference of two perfects, or a perfect square trinomial, which it is. So the rule for this one, so I erased it, but a squared minus ab plus b squared. This time the only difference is that our binomial that we create, we have to have subtraction there because the only way to multiply out to a positive number but add up to a negative number is to have two negative numbers. Negative times negative is a positive, but a negative plus a negative is a negative value, okay? So when we go to do this, we're gonna go do the same thing kind of, right? We know it's gonna be a binomial times itself, so we're just gonna write it as a squared. Square root of 9 is 3, square root of x squared is x, square root of 25 is 5, but my middle term is negative, so in my factor, I need minus instead of plus. Okay. So in the same vein, factoring a difference of two perfect squares. So this is essentially factoring a trinomial where the middle term is 0. That's essentially what we're doing here. So we can treat it like a trinomial, and we can rewrite it. X squared plus 0x minus 9. So what I'm wondering is what two values multiply out to 9 but add up to a 0? Well, 9's a perfect square, right? So something unique about 9 is that it's 3 times 3. So if I look at 9, okay, well 9 is 3 times 3. It needs to be negative, so let's make one of these negatives. Well, when we take something plus its opposite, right, a number plus its opposite, we get 0. So I can factor this guy, right? X plus 3, x minus 3. Now, when I multiply it together, my middle terms will be plus 3x minus 3x, which will simplify to just 0, all right? So we can apply the same idea over here, but we do need to do a little extra work because we need to factor a GCF. So I'm going to factor that out. We have a GCF of 2. Okay, so it is important to note that this only works when we have a difference because the only way that we're going to get two terms to cancel out is if one's positive and one's negative. All right, when we factor. So we can look at this and we can apply the same idea when factoring. So we have 2. And let's look at our binomial. So our first term is always the square root of the first term, just like it was in a perfect square trinomial. So the square root of the first term here is 2x. Square root of the last term is 7. The difference is that now we have no middle term. Our middle term is 0. We want it to cancel out. The only way a middle term cancels out is if we have opposites. So one positive, one negative. The last thing we're going to look at here is when we're asked to factor completely. So this is when we're looking at a polynomial and all it says is just factor it, right? So it doesn't tell you what strategy to use, doesn't tell you anything about the polynomial other than it wants it factored. So just like before, the number one thing you look at is for a GCF. Always check that out first. So in this case, I'm going to factor out a GCF of x squared first. And then you want to look at this and determine, are you dealing with a binomial or a trinomial? So in this case, I'm dealing with a binomial. The only way I currently know how to factor a binomial is if it is a difference of two squares, and this is, right? So I can factor it. So I keep my GCF with me. A difference of two perfect squares factors into two binomials. Square root of the first term, x to the fourth, the square root of x to the fourth is x squared. Square root of the last term, 81, square root of 81 is 9. And then it's a binomial, so I need those middle terms to cancel out. So I need one positive, one negative.
So we want to just double check that we're fully factored, and in this case we're not. That x squared minus 9 can be factored a little bit further there. So we just want to keep factoring that. So x squared plus 9 are going to stay the same, but x squared minus 9 is another difference of two perfect squares. So we're going to factor it into x plus 3, x minus 3. So let's take a look at this one. And again, we have a GCF, and actually, again, it's x squared. So let's factor that out. And we're going to be left with x to the fourth plus 7x squared plus 10. And now we have a trinomial that we need to factor. So x squared is going to stay the same. We're going to factor this into two binomials, and we're going to factor this very similar, even though it's of an x to the fourth, but instead of asking ourselves for the first times first, what is x squared, we're going to ask ourselves for the first times first, what is x to the fourth, just like we did in the other one. So x to the fourth is really just x squared times x squared. So that's going to be our first term. And then we're going to treat it like any other binomial here. And we're going to say, what two numbers multiply out to 10, that then when we add them, we get 7. And that would be plus 5 and plus 2. And we can always just check here for that middle term, make sure that we're still good since our exponents were a little bit different here. We're going to have that 5x squared and that 7x squared, or that 2x squared, which will give us that 7x squared. And just like in the last one, we want to check to make sure we're fully factored. Can't factor x squared anymore, can't factor x squared plus 5 anymore, and we can't factor x squared plus 2 anymore, so we're done.